Okay, so one of the most interesting aspects of derivatives is to analyze how a function is behaving close to a point or around a point. Okay, and so they allow us to analyze the local behavior of a function. Okay, in order to do that, we need to first introduce some definitions, and then we'll see some theorems and results that use derivatives to understand the behavior of functions, right? So first of all, we say that a function f has a local maximum at a point A of its domain if there is some interval, okay, and an environment of A minus delta, A plus delta, such that f of x is smaller than f of a for all x in that environment, okay, something like this, right? So that means that point like this, okay, this is f of a, and around this a very short, it doesn't matter if it's short or large, a very an environment of this point A, every f of x is smaller than f of a, right? Smaller or equal. It's the same thing with the local minimum. It's just that instead of being a point around which all of the values f of x are smaller or equal, in this case of the minimum is greater or equal. Okay. We can collectively call local maximum a local minimum, local extrema, because there are extremum points, a point where a function reaches an extreme value, right? And if local extrema remain extrema for all x in the domain of f, they are absolute extreme. Okay, so then we can talk about absolute maximum and absolute minimum. Okay, and obviously there's only one of both, right? Because in order for a function, for a point to be an absolute maximum, it has to be greater than every other value of the function for the whole domain, right? So there's only one of them. That. Okay, and also for the minimum, right? Well, there's an interesting characterization of extrema based on derivatives, right? And it comes from this theorem, right? If f has a local extremum at a point A, right, where it is differentiable, then the derivative at that point is 0. Okay, and that ties in with the geometric interpretation of the derivative that we had talked about. Is that the derivative talks about the increase or decrease of the function at that particular point. Well, if the derivative at that point is 0, that means that the function is neither increasing nor decreasing at the point. So that means that's an extreme. Okay. The proof for this is easy, right? If we have a point A, okay, which is a maximum, well, that means that f of x minus f of a, right? If we come from the left, right, like this, well, f of x minus f of a divided by x minus a, if we are getting close to it from the left, right, it's going to be positive, right, because the value of f of x is smaller than this, so then the numerator is negative, and then x minus a is also sorry, it's also negative, so this is positive or equal to 0, right? Now if we approach the maximum from the right, this is the limit of this quotient is now the numerator is now negative or equal to 0, and the denominator is positive now. So now this quotient is smaller or equal than 0, right? So, but now the theorem says that at this point A, the function f is differentiable, and because it's differentiable, that means that these two limits must be the same, because the limit when x goes to a of f minus x, fx minus fa divided by x minus a is the derivative, right? So that means that these two limits have to be the same. But because this is greater or equal than 0, and this is smaller or equal than 0, that means that the only possible value for the derivative is to be 0. Okay, these two limits have to be the same and equal to 0. Okay.